Hello all. So today, this is what I'm including as one of the part 3 projects of learning the art of electronics. Some changes that I've done to the power supply project. In particular, I've added a voltage regulator. I believe was chapter 11. So it's right there. Now I'll escape. I zoomed a bit here so that you can get a better view of it. So I decided to use the LM317. That was primarily out of temperature concerns. The regulators I had in stock. Um, the other regulators that I also had in stock were all too small. Um, so they would have heated up too much because I wanted this to be adjustable from 9 volt or from basically taking it from 9 point something volts under fully loaded conditions all the way down to 3 volts. So the power equation would then be, since we want this to also be up to 100 milliamps, you got PVI, and if we say that this is going to be, like in the worst case scenario, we're outputting 3 volts, 100 milliamps, that means that we have a 6 volt drop or more. I went and think, yeah, so like if we do a 6 volt drop, then we'd have zero point 0.6 of a watt being dropped against across here, and some of them were basically wouldn't be able to take that without, like, some significant heat sinking or otherwise. I did also buy, or I included in the BOM, a heat sink for this just to add a little bit more. I don't think it will need it though. But let's sort of go in to the design of this. So I picked first we'll talk about these resistors here. So I will throw up the equations on here. I have them in my notebook here, but basically we have R2 at 2K, R4 at 2.2K, and then this R5 goes from 0 to 10K, so that makes the adjustability. Um, the output of the LM317 is defined as Vref, which is the reference voltage of 1.25 volts, multiplied by, or like bracket, multiplied by 1 plus R4 divided by R5, or R4 plus R5, sorry. I don't know why I put divided. That should be plus. R4 plus R5 divided by R2. In the minimum voltage scenario, we would have 1.25 volts plus 2.2 divided by 2 times 1.25 volts. That would work out to be 2.6 volts. In the maximum output scenario, we would have 1.25 volts plus 12.2K ohms divided by 2K times 1.25 volts. That turns out to be 8.9 volts. Now, I did put this on the breadboard and I measured it was actually 2.6 volts and 2.9 volts. Or 9.1 volts, I mean, outputting. But anyways, that's the calculations there. Could go into the power calculations, but I think I actually did cover that in a short video that I did. And later on, I may actually make like sort of a PowerPoint presentation for each of these projects. But for now, I think we'll move on to where I decided to put my test ports. So basically, I decided to put another test port here and here to measure the voltage out, like the final voltage out. And then over here, I put a test port for the current that goes through the adjustment area. So this, because there will be some current coming through this I adjust. I just wanted to maybe measure that. Then that will be an error term. Then it will also have this current coming out that way too. We'll just see. We'll be able to see what that is through that J9. Let's go over do this one. Look at this one. So this is, as you well know, the PCB layout of the power supply. Now, if you watched the previous design video, I did the layout in it. This one is edited. It's different from the other one. But in that one, I had trouble getting these, like, to make separate pores for this. This time, I didn't have trouble with it. Alright, there's it's complaining that this footprint doesn't match in its library. But you see now I was able to make the proper pores for it this time, which is nice. Over here, and I did a pour for each AC one just to make sure that there's lots of stuff there. Now let's just go over here. Let's just look at the front copper layer. So, okay, I'll delete all markers just so we're not bothered by it. There we go. So we're at the front copper layer here. You can see here I have the one ground pin that isn't connected, like at the bottom, so they wouldn't get to the ground plane. I put a bunch of vias there. Now, I know it looks haphazardly. The vias are haphazardly put there, which they sort of are. I think they'll do their job anyways, though. Then we see we have the AC after there. All the ones out there. This is, if you remember too, we had problems with the with that, which maybe it would be useful. We could just actually double check. So you see here, I'll show you the pin diagram quickly. Right there, we have 3, 1, 2, 4. Let's go over here and check. Yep, we have the right ones there. That's the minus, plus, and then 2 and 4 are the AC ones. So we got that good this time again. Or not again, we got it good this time. Because before we didn't have it good. So we go over there. That's connected to ground on the bottom. And all of these are basically connected together. This is the initial rectified, unregulated DC voltage. Yeah. So now we're going to go over here and we're going to get into the rectified DC voltage. So we got the power output right there. This is the adjust. As you can see, I did that oddly. Guess I connected. That doesn't too much though, I think. Just look, this looks odd to me. I think maybe could have put this R2. I should have placed it maybe a bit better. So that it could get to the power output easier. But I think this will be fine. I'm just thinking about what I could do differently there. And if it's worth it right now. No, let's move on. So you see here, this is connected to the adjust pin there and to the power output there. Then it goes through R4, which is 2.2K. And then that R4 goes into this trimmer resistor, which is 0 to 10K here. And then that goes through there into this PPK2 port. I called this current from voltage adjustment, and then that goes to ground. Then this is the other test port. Let's now turn back on the back copper layer, turn off the front copper layer. At the back copper layer, you can see we effectively only have the ground plane. So I think that is it. Thank you for watching this video, and I hope you tune in to future videos.